Hello everyone, in this video we're going to cover the notes on section 2.3 and in this video we are getting into the derivative. So to focus our discussion, I want to go back to the topic of secant lines and tangent lines. So if we have a graph that I'll draw here, here's maybe our graph. We've seen before that if we have a secant line on our graph, that's just going to be a line that intersects our graph at two different points. And what we've seen before is that the slope of a secant line is the average rate of change of that function over a given interval. So typically we can label our points here A and B, our outputs f of A, f of B, and the slope of the secant line between those 2 points is equal to the difference of our outputs over the difference of our inputs, and that is the average rate of change over the interval from A to B. And then now, as we bring B closer and closer to A, so as our secant lines move further and further, or are defined rather over a smaller and smaller interval, we approach this beautiful line that intersects our graph at just 1 point. And that line is called a tangent line to our graph at the point. So let me draw a new graph here. So again, as our secant lines approach a specific point on our graph, the line becomes what we call a tangent line to the curve. And here I'll just kind of focus maybe on a similar point as what I used before. And now the slope of the tangent line is the derivative of our function at that point. So I'll back up and say the slope of tangent line is what? Well, how do we compute the slope of this tangent line? Well, one method is to bring, or similar to computing this average rate of change, compute an average rate of change, but have the interval over which we're computing that average rate of change shrink so small so that we only compute the rate of change at an instant. So conventionally, let's let x be the point that we're wanting to focus our tangent line above. And so we can call the size of that interval, well, x plus some amount h. So up here we have f of x. And over here on our graph, we have some f of x plus h. So to compute that derivative, or the slope of the tangent line, that is the derivative, we compute these slopes of secant lines that approach our tangent line. So if we did have a little interval here, x to x plus h, the slope would be f of x plus h minus f of x all over just h now, because our denominator was going to be x minus, or x plus h minus x. X's cancel and we just get h. So now that would be the slope of the secant line between the points x and x plus h. So if we want to take that instantaneous rate of change, we need to find this difference, or this quotient, as h goes to 0. So the slope of the tangent line can be computed using the following limit, which we'll see in a little bit more detail here in the next bit. But compute this limit as h goes to 0. And typically this setup here is called the difference quotient. So we will be seeing some of that language coming up in this section and in more sections of our notes. All right, now with that, we're going to continue filling in our notes. using this following box. So this is just going to introduce for us some notation. So m sub tan, m is typically used to denote a slope. And then sub tan, that's just telling us this is the slope of a tangent line. So the slope of a tangent line, can be computed with this following limit that we just saw constructed. So that is the limit as h goes to 0 of f of x plus h minus f of x over h. And the reason why we just went through this little discussion over here is because I really want us to see this limit as just being a limit of slopes, a limit of secant lines as that secant line approaches our tangent. So even though this might look complicated, there's really nothing new or scary going on here. We're just taking, as we've seen before, change in y's over change of x's. So further in this box, we just see a bit more notation. So we have all these 4 different things that are all equal to each other. And in fact, they're all equal to this limit as well. So we should have a big equal sign in between these. But this just emphasizes different notation and ways of saying the slope of the tangent line. So let's go through these in detail. So here we have our function notation f with a little comma or apostrophe of x. So this is said f prime of x is how we say this notation, f prime of x. So that apostrophe is pronounced, or is we say it prime. And so this is just a shorthand notation for this limit. Another way that we can describe the derivative is this notation, dy over dx. So some people, when they see this dy over dx, they just say dy dx. But we use this notation if we write y is equal to our f of x. So if we're treating that output, or if our notation for the output of f of x is y and our input is x, then we can also write that derivative dy dx. And we say to kind of more formally how we describe or say this fraction here is the derivative of y with respect to, so that d with respect to x. So that dx on the bottom just tells us which value or which variable here we are changing. So here, as I had written, this is another way of saying this limit would be taking a limit of the change of y's over change of x's. And that input that we're varying in this case is a x variable. So that's why we say with respect to x. And then we saw this already, m sub tan. That's just, again, another notation for that slope of tangent line, which is also equal to the derivative. And formally, we would actually say the derivative of our function f at point x. So the derivative, in what we're seeing so far, is always the slope of a tangent line, or the slope of a tangent line at a point.